So this is the host is here, and the card is here.
Okay. Yeah.
It's a terabyte drive.
Are you busy on that drive?
Yeah.
I am. I requested last night. I was like,
Yeah.
What is your first name?
It was over Harvard.
You want it?
So I took the action train.
Oh, so that machine has a bias to let you boot on
And it was
it.
Oh, Harvard.
Yeah, and so
Some machines don't like to
the
do.
cops don't feel like investing in really hard.
So what's this?
It's tough to get
So
arrested.
we go to 12.
But it,
Depends on where you go.
well, it was all good.
So
Because the only thing was is,
so what's your boot?
First of all,
Okay, before we start, we're gonna Tony Dash from Free Computer Labs. And Julian
Oh,
does,
just so you know, we're live on YouTube right now.
Julian does free computer takes discarded computers, restores them, and then you give them away or what?
Basically, our process is yes, to receive all computer, new computer, and to teach people how to recycle, let's say recycling or rehabilitate them. I don't know how to say, like restore them.
Yeah.
Restore them and use it with free software. So it's an educational program for people that don't have a computer at home to take the computer that somebody else is not using, somebody is that potentially use. That's we started this weekend in Cambridge in Industry Lab, and we have a launching event, and we start the classes. So we are receiving material, any kind of hardware or computer that we can use. Like we will come a computer from 10 or 15 years ago. It's okay for us, and also memories or hard drives or CD players and.
HP laptop that I could give you.
Excellent. So I just write the name of the project is. Okay. Computer apps.org. So here we come with kind of information. You can contact us to be on your hardware, and where is the launching event?
Okay.
Okay, thank you very much.
Thank you very much,
Have
Julian.
fun. Happy.
Okay.
Actually, I use the software for the
Okay. Well, we actually did that with the Boston Computer Society quite a while ago. And it kind of went out of style. And then when the Boston Computer Society went out of business, and then this sounds like a good effort. And I'll start our speaker in a couple of minutes whenever Brian's ready.
I'll go.
Ready to fly.
Okay, and I'm going to go outside and handhold Rocky for a few minutes.
Good.
Okay. Do you want both screens on, or?
Just plug in, let's see, the HDMI connector. And we get, if we're lucky, this will work.
No video signal?
No. We have conversations, and I'm really interested in small ways to generate electricity.
Yeah, but you're not thinking, you don't want HDMI. We're not getting on either screen.
There's someone else who's doing this.
It was working earlier on
Aaron's computer.
Aaron's computer.
That's because we put it on.
Yeah, I'm doing it on both right now.
On both? Okay.
Here I went through.
Laptop HDMI.
Right there. Yeah.
Wow, this video is extremely jerky. Something tells me we're not gonna be able to retire the camcorder.
Right, I didn't go in to see, the military's already
Do a functional F8 or something like that. It's up there.
flexible fabrics and have flexible thin film to a fairly high. Can you tell you anything?
Yeah, I'm not seeing anything from you.
Are you?
Is it connected?
Yeah.
Laptop, HDMI.
Mhm. Yep. I could try, but that's just the way it was on in the other, in Aaron's computer. No.
No, it didn't work on.
Oh my God.
I think it'll start.
Different,
Screw up.
you know, very
Let me just try this.
when we got, it was still vacuum tubes. And then when I was in the 8th grade, I found my first transistor.
Said no,
Which was in 1996.
no video signal.
As computers with analog.
This has a GA connector.
When they first used digital over Harvard, it was to control the analog computer. The simulation of students and analog the controls, resets, and runs and speed. All done digitally.
There it is. Okay, we're live.
So,
There we are.
It's making this. Good, thanks, Chris.
And then years later, I found out about Intel was in 2008. And I knew that the world that my principals had been talking about was really going to happen.
I'm surprised.
Okay, I gotta admit, this is gonna be a pretty lightweight presentation. That's actually legitimately the first presentation I made in just Linux, which is a scary thought. Typically, you know, I do it in Windows and stuff like that, and I should have brought the Windows machine tonight for a different reason, which I'll get into. But anyway, so here we go. I guess the theme of the evening's discussion is around embedded systems and SoCs and systems on chips, and we're lucky to have the real deal follow me, which is Kurt and Arun, and I'll kind of try and connect into that. But so here's what I'm going to talk about. I'm going to talk about some existing low-cost, basically systems on a chip, microcontroller types of things, and potential application environments in which they might be utilized. Right. So. Just before this, I went over to a talk at Boston University, which Robbie actually kindly pointed out, and it's that kind of a guru guy talking about vision systems, basically photonics at the BU photonics lab. And here he was. This is I'll clean this up in the thing that I finally sort of distribute. But he's the chief scientist at this vision systems agency, basically, that does a lot of development work on behalf for the Army with DARPA, and he's been doing the vision system stuff. Have people done vision types of applications at the level of circuits and chips and stuff? And it was there basically at the level of the long wave infrared, short wave infrared, for seeing stuff up close. And one of the coolest demos that he showed was basically taking these different types of infrared, each of which has strengths of the types of attributes that it can see in different settings, but then they fuse them together and you get a much better image out of it. But he said one of the most interesting applications of it, so he's doing stuff for the Army, but it turned out that some of the coolest things that they've seen come out from their essentially fundamental research is in the gaming communities and in the adoption of this like thermal imaging technologies to cell phones, to simple cell phones and people are using these technologies for simple things, like finding out where the heat leaks are in your residence, right? And basically what his vision was essentially of embedded technologies. As these technologies become lower cost, and so he was essentially challenged with taking this fairly cumbersome energy sort of starved technology and expensive technology, and basically bringing it down to the level where every soldier could potentially have this on their helmet. Or and so he kind of went from maybe a multi-$1,000 application to one that was under $500 a pop. And a lot of this was done by getting the stuff onto. And Rod, you could talk about how did they do that at the fabrication level and at the silicon level and stuff like that. But through progressive improvements in these things, and this is where I kind of segue into one of the talks tonight and a little bit of a prelude to a talk that we give next month or sometime later. So one of these are launch pads from Texas Instruments. They were, this one probably is about $20. These are $20, $30 types of systems that, system on a chip or system on a board. Basically, this particular one actually has an LCD display on it. And so it's got some kind of microprocessor, microcontroller, and what's a microprocessor versus a microcontroller. Anyways, it's got something that you can program that's got onboard flash memory and computational abilities, and it's also tied into the LCD screen, right? So this is an MSP430 based chip. Well, what they've come up with, literally like just in the past week or weeks, is the MSP432. And so they've moved from a 16-bit essentially instruction set to a 32-bit instruction set, which you might think is maybe not a big deal, but it really is, I think, probably fundamentally a major shift. So you've got a very low power, energy efficient processor. Haven't had a chance to test it yet, but it's moved from 16-bit to 32-bit, but still challenged by all the same parameters of low cost embedded systems, but much more processing capability. Okay, so this is where it's gone from P430. They're migrating to the MSP432. Another product that Texas Instruments has had available is this sensor tag kit, which I've certainly shown in the past. It might have a half dozen, 8 types of sensors on it for sort of motion, as well as temperature, as well as light sensitivity. And you can run on a little battery, and you can program it. It was quite cumbersome to program. I might have gotten this one. I'm not sure when, and looking back to that, maybe 6-8 months ago. Well, they've come out with just a new one very recently. And instead of having like 6 or 8 sensors, it's got 10 sensors. The energy efficiency is even much greater. It's got a new ARM Cortex M3 on it, so it's got, in addition to having Bluetooth on board, this little chip, it's also got SoC added to it. I don't know how general the radio is in terms of if you use it for other things, but it's also programmable from code to code. And whereas the previous one was kind of constrained by a little bit more proprietary model, it's like IP rights that they had to declare and stuff like that. But again, what we've seen is something's gone from pretty compact. So these are the same kinds of things as what's the Apple technology, the beacon stuff. Walk into a store and it knows that you're sort of in the record aisle as opposed to in the groceries aisle. Similar sort of beacon technology is basically on board with those, right? So much better battery life, much more powerful, computer instruction set, and also better radio alternatives, right? Price is still the same. I don't know how much it is, but I think it's maybe $30 or something like that. And then all of these things, we're doing a little bit of experimentation with some of these, but the way I'm powering them, which is pretty cool, off these little, 5-volt USB things, you get $15 or $30. And you can run for a really long time. So the way these work, I had it set up before I rebooted, but I could jump into it if people are interested. You essentially have a programming environment. It's a C-like, it's Arduino-like, for kind of throwing out the buzzwords. Very easy to program, very easy to get little snippets. And so once you flash the board with the program, and these boards have sensors in their own right, gyrometers or accelerometers, and temperature types of things. And all these pins are sort of accessible in the same way that an Arduino board could program. And then you just plug it in, and it boots up, and then it just it loops, sort of perpetually, right, until the battery runs out, or you push the button and shut it down. Okay, so the deal with this, the CC3200, is that it's basically a single task, single program board, right? Well, the new thing that they have just come out with, and that which runs the first board that they have it's supporting is, sorry that there's overlap there, is the MSP432 board, and it's a real-time multitasking operating system running on these little tiny boards, right? And there's a development environment that goes with it. The development environment is free. So again, so the MSP432 chip, or they call these launch pads. So TI, they sell the chips, they sell the components, but then they nicely put them onto these launch pads, which are basically evaluation boards. They're also reference design, they're sort of really available. So they have the CC3200, great board, it's got onboard Wi-Fi, easily programmable. We've done some pretty good experimentation with it, but it only runs a single task, right? So if you, for instance, want to do a simple thing like have 3 different LEDs blinking at different times, you'd have to write the code to keep track of the state of all the different LEDs, what's on top. Fast forward to the MSP432, or the Energia multitasking platform. Now all of a sudden you've got it remains real time in the sense of what real time can be, where you've got some software interface there, but it's also multitasking. So each one of the programs, what you basically do is you'll write 3 programs: one to blink LED 1, one to blink LED 2, and one to blink LED 3, and then you just kind of set it off and run. So now you've got a multitasking, sort of operating system, not threaded, but almost through real time. Does that make sense? People have questions on that? So the state of that right now is that if I happen to have, I have an MSP430, I don't have an MSP432. What they're basically doing is they're building in support for the different boards just based upon time and resources available, right? The first one they chose, the MSP432, 32-bit, probably get a little bit more horsepower, and it's a nice way to show off. They have a beta of the support for CC3200. It's available for Windows and Mac OS, not for Linux. And of course, tonight's the night that I brought the Linux box. Otherwise, I would have demoed it. But next month, I'm hoping with John and Jerry's support, we'll actually do a deep dive into this, where we'll have sort of multitasking, real-time applications running on this. Again, the Energia environment it's very familiar for people who have done. How many people have done Arduino stuff? How many people have done C or C++? It's pretty familiar as far as that goes. Okay, so the sensor tag, again, there are 2 themes here. One is that this stuff is moving really fast. Yeah, question.
When you sit down to work on one of these and you have your laptop, how good is the development platform in terms of ease of use?
It's I would say it's good enough in the sense that if you've got so for a quick footnote, might have mentioned before, don't mean to dwell on it, but so in January, myself and others, Kurt participated, and some others, we did an independent activities period session here, and we did actually 2 of them. One was a week long, and one was a day long. And the week long one was basically all about IoT types of things, right? And the day long one was focused more on just Wi-Fi types of things. There were some total of about 100 MIT students or alums or MIT affiliated people who participated, many of whom had no prior, surprisingly, maybe, no significant prior programming experience. They had some, but very basic stuff. Every single person got through and accomplished pretty amazing things. So the point being that the tools that are available are they're not sort of 10th generation in the evolution of things, but they're adequate. They're basically, you've got a graphical user interface environment, you write some code, you're doing a lot of debugging by writing out line, item types of things, messages to the screen. And once you've got, and it does check, I think, for basic compilation stuff. And then you just basically hit a button, it uploads it to the boards, and then it starts running. So the problems actually you encounter are more platform that's like particularly USB. I heard people talking about USB earlier. And, you know, the USB is kind of, it's a little bit hinky on the Linux stuff, right? So sometimes you got to, in between iterations of the program, you got to reboot, or you got to restart, or you got to unplug it. Or the favorite thing on this, and it may vary from Ubuntu to, you know, your choice flavor of Linux. On this one, what happens is kind of good for two different boards to work with, and so you pull one out and you put the next one in, and then for some reason it increments the USB number, so it refers to the second board, and each time you basically have to point the editor.
I got a good idea.
Okay, so
Thank
Is energy of the development environment?
So Energy is effectively Texas Instruments, a brand on the Arduino, user interface, or IDE actually is more appropriate. So in fact, as we talk, I'll bring it up because I should just.
And that runs under Linux.
Yeah, and it runs on Linux as well as Windows as well as Mac. So here, I'll just kind of show you how. So this is the particular build that I was, working with, and this, sort of unfortunate how you have to start it up. It's got like, an icon and stuff like that on Windows. I have not used it on Mac. But so what it's doing is, so it's just brought up the editor, and what you'll see in the in the next generation of this, with this you can create new tabs, or so actually I'll show you a bunch of examples. So here, if you just want a simple blink example, you can bring it up. If let's see how we create, you can either create new ones or you can create new tabs. The way the new version of Energy works
Is it on the screen up here?
Oh, where did it go? Oh, sorry about that. You guys, it looks good to me. How do we? Hang on a second.
There it is.
Okay, I'm not quite sure why. Of course, the good news is you can see it and I can't. So it's sort of over here on my screen right about now.
You can't see.
But that's okay. I guess I can see it.
Well, you can see it there.
Yeah. It's on the walls now. It's moving.
It's on the back monitor too.
I'm not quite sure. Oh yeah. Okay. Then just look up there. Real things. Anyway, so it's not a sophisticated thing at all. And then what you see in the bottom parts down here is you'll see output as things run, as things. You'll actually see the compilation of it as well. It's open source as well, so you can kind of get in there and dig and find out what the and there are a bunch of libraries. There are different libraries for Wi-Fi versus a few other common types of things. So generally speaking, it's very easy to get into. These boards also they work with Code Composer, which is Texas Instruments version of things. The version of a compiler. The other thing is basically under the hood, although I haven't completely torn the thing apart, of the Energia, which, and I presume also of Arduino, is essentially a GCC compiler. So it's, that's what they're kind of building on. All these boards they're ARM-based chips kinds of things. Okay, so what else is in here? Oh yeah, okay, one other fairly important thing to point out. This was the question I asked the developer of Energia, the lead guy, today. And it's kind of, I'm interested in the C3200 because it's got an onboard radio. The MSP430 doesn't have the onboard radio, but it's everywhere and it's super low power, and it gives you access to all the deep sleep states and things like that. So if you're doing smart grid stuff, or if you're doing energy harvesting types of things, or if you're doing even sort of building information management kinds of things, where energy tends to add up over time, the MSP430 is kind of a great chip. But what they do have for the MSP430 is they have these things called booster packs, which, just like Arduino has what do they call the add-ons? You have the shields, right? So same way, it's got, kind of a standard configuration. You just plop it on. And so there's a radio booster pack for the MSP430. So the question to the developer of Energia was, first of all, does the current multitasking or real-time version of it support the radio stuff, right? And so basically the good news is that yes, it does. But then the next question, which I kind of have to, I guess, prove to myself, is let's imagine you've got multiple applications running in this real-time multitasking environment, right? And you want to share the radio. You want to share the, the network connection. How do you do that, right? And so on one hand, it's, if you just have a single task, single threaded, that's all you're doing is talking Wi-Fi, seems pretty straightforward. But once you introduce the, sort of the multi-partitions or the multitasking stuff, and we'll dig into that next, next month, I think. So the simple task would be, you've got, now all of a sudden you could have one board multitasking and controlling a whole bunch of different devices, essentially in a fairly clean and parallel environment. But back to the point of the the embeddedness of this stuff. The other beauty of these boards actually is that they're highly configurable, kind of out of the box. All these things are jumpers. You can just pull them off, and by pulling them off or putting them on or reconfiguring them, you can do different things that allow you to essentially flash new images onto the boards, or actually disconnect and disable certain portions of the board. So the other thing is some of the boards, if you didn't need to use this LCD, for instance, and you wanted to disable it, hypothetically, you could sort of disconnect that circuitry so that it doesn't drain any of the energy. And one of the other neat new things in the MSP432 is they've done a lot to, even though it's super energy efficient as it is, they've done a lot to both tighten that up and also give you much more visibility, as I understand it, into essentially the energy consumption in each of the different components of, and so if you're developing an embedded system where energy is a limited resource, which oftentimes it will be, those are tools that you really, if it's not sort of instrumented onto the board or into the development environment, you're kind of at a loss for it, right? So, okay, so you get kind of a look at that. That's what and you just, there are a bunch of good examples. It's very familiar if you've done Arduino stuff. And after a very basic sort of startup phase, you'll be pretty proficient in it, I would think. Let me just go back and see if there's any other. Now I'm wondering, did you see any of the slides that I had up before?
Yes.
You did? I wonder how that was. Okay, let's see what we got here. That's interesting. It came back. Okay. Interesting. Here's a comparison to see if I look. Actually, instruction cycle. So they've based one to two instead of 1 to 4. So clearly a 3-stage pipelining. Again, all this stuff is going to really improve the energy efficiency. Good thing. Interesting, they have an integrated floating point unit as well from that. So previously what they had is some boards had a hardware floating point unit and some boards didn't, and you kind of had, it looks like they've just got it all in the chip.
Do you know what the RAM and ROM limits are in 432?
I don't. Yeah.
I assume it's greater with the 32-bit.
Yeah. I assume it's pretty linear.
So they've already done tricks to extend beyond the original ones were 64K maximum, but they've got already at 430s with some point bank switching or something, so it may not be greater.
Yeah, I guess I just say that it's funny. Last night I got together with some of the early Macintosh development folks and from the Boston Computer Society, and John would certainly know them, Mike Morton and Tony Nelson, and different.
I haven't seen those guys in probably 20 years.
Haven't seen them in a long time, and so we reminisced a little bit about the 128K Max and to a certain extent the amazing stuff that you could do with sort of very limited resources. So, again, it's a good point. Probably with 32-bit, you do open up the memory space. I'm assuming it's linear, and if you wanted to build an embedded system using this as a chip, you just spend more on memory.
But you're just executing C code. You're not running an operating system on it, right? You're just compiling code and system run.
Right, so that's a good point. So today, on the MSP430 or on the CC3200 or everything that I've personally done to date on it, that's absolutely the case. In fact, you could only take one of these applications at a time and run it. And when you're done running, that hello world, you got to hit the stop button and move on. However, as of today for the MSP432, and next month when we'll demonstrate this on the CC3200, you actually will have, a real-time operating system layer. At this point, I'm not clear how it's architected, but I'll know by next week. But you will have a very thin veneer of an operating system below you. And so, and has anybody ever used the TI RTOS stuff or free RTOS?
All of those ones can run the RTOS API, and you can just have, as long as the processor speed handles it, then you can have multiple features.
Yeah, so that's a good question. How much will, in terms of the performance, will you see just based on this? How well has that been tuned? And also what, some functionality in terms of file system architectures or wireless stuff or things like that. So next month we'll do sort of a walkthrough and maybe recruit you to do some of it too, of what this real-time operating system looks like, what the componentry is, and how it sort of applies on these smaller boards as opposed to on bigger systems.
Very quickly, is there a facility in the new Energia that allows you to change clock speed and voltage in order to control power consumption?
That I don't know, but that's a good question.
I'll go look up.
Yeah, the question that I've asked, and I'll ask them again, that's somewhat of a different way. The one thing I would like to be able to do from Energia, you certainly can do it from Code Composer, right? So where you're basically in at kind of a binary level, and you have direct control over the sleep states and the various sleep states and things like that. I don't know if you actually can dial back the speed because that has lots of other considerations, but it may be a sort of a throttle thing where there are different levels at which you could stair step function.
Thank you.
Yeah. Any other questions? Yeah.
The wireless support you mentioned, Bluetooth Low Energy, and does it do Zigbee as well?
Yes. Yeah. The MS-2432 does do Zigbee. So they have three other chips. Three other products. One is the 6 low pin, which I've actually seen listed on the new slides. Another one is sub 1 gigahertz, which I really am interested in for reasons that might not be. Anybody do like our sort of remote control, radio control, either flying things or running things? Okay, so one of the things is like 433 megahertz controllers of quadcopters, or you get much greater distance and more controls. And so I'm wondering to what extent you can essentially program that kind of thing using their sub 1 gigahertz chips. But the way they've implemented it, which is I think pretty clever, we could probably dig into this more. They basically have one chip architecture, one radio architecture, and then they've implemented these different protocols essentially in software, from what I can tell. So instead of having different chips for each of these, 6 low pin and Zigbee and BLE, which is 2.4 gigahertz, and it's sub 1 gigahertz, they've got one chip hardware architecture, and then they've essentially got different protocol steps. I don't know if anybody can confirm or deny that, but that's what I believe to be the case. So it may be the kind of thing where chips that we have today that only support, for instance, Zigbee and BLE, tomorrow actually and one of the chips that they do have, which I probably can pull up, they do sell it. It's kind of like the higher end chip, and you can do any of the protocols on that chip, and they essentially have just different libraries for each one of them. So it's kind of like software-defined radio with essentially hardware support, I think, for it. We'll know more soon. But indeed, the case is that they do have some, for instance, the Zigbee and the BLE are both supported on the same chip.
Just a quick comment on the hardware sensors guy point of view there. It's very interesting that this almost feels like covering the very last mile, as we say, to me, in the sense that we've had computers for a while, but only until we have into these things that we can actually take a computer and interface it with sensor devices, accelerometers, heat sensors, and the like. And this hasn't happened before, and the significance of it is going to be very interesting to see, because a device that was before cheap and not worthy of consideration because of its quality may suddenly become quite powerful because of the processing power that's behind it, because it's connected to the internet.
Yeah.
So it'd be very important to watch how these systems are being deployed, and if the cheap sensors can actually become the main way that sensors are used as opposed to expensive high-end stuff now, simply because there's so many of them, you process the data easily, everyone can access them.
Yeah, I think the whole sensor thing is just going to explode. The reason I kind of started off the vision thing, although it was maybe a little bit scattered, is essentially cameras are just sensors, right? And they just pick up different sort of frequencies or physical sort of matter that's out there. But also the different kinds of sensors that are available: acoustic, sound, motion, heat. There's just a lot of, and there are a dime a dozen. Which is, and you really can connect them to these things fairly easily. There's most of the sensors I've gotten, actually, I think it probably come from Hong Kong, but you can get them for all sorts of sensors for under $5 a piece. And the kinds of applications that people did in this program in January, one was like a leak detection sensor. Fortunately, we're sort of on the other side of the winter that we've all had, but for anybody who knew someone who had frozen pipes, and I knew a couple people who. And one of the projects these guys came up with was to just first of all sense the temperature, pretty simple, and then to sense moisture, right? And if both of those things are sort of in the danger zone, then actually you can easily communicate. And this is a big thing. You can easily communicate either via a Bluetooth message to your pocket phone, or via an email message or a text message to inform a person that hey, you should pay attention to this. And so I'm convinced that it's within the reach of everyone in this room. That if you had, and the other thing is, all the things in this bucket didn't cost more than probably $250, right? And so for any of us who bought a Mac 128K when we first did, it was $2,500. I mean, we talked last night, and then I'll get off unless there are any other questions about my first Anybody remember the Mac Bottom hard drive for the Macintosh?
Oh yeah.
How much did you guys pay for it? For 5 megabytes. 5 megabytes, not gigabytes. Do you remember?
I used the one at BSS office. I didn't pay for it, so I never knew the price.
Well, the beauty was you could kind of daisy chain them too. Anyways, do you remember?
I don't remember the price. The first one I had was an HD20. Interesting.
Yeah.
Was the manufacturer Mac Data or somebody?
Mac Bottom. It was a company I think out of Florida. It's just an entrepreneur. Anyways, my recollection is $500 to $800 for a 5 megabyte drive. And so now obviously people have people probably have gigabytes of thumb drives in their
What year was that? Because I seem to recall it being more like $5,000. But that might have been a few years earlier.
It could be, and I'm just trying to put those memories out of mind because it's just obviously those that's. But it's another good point, which is the obsolescence factor in all these things is tremendous. And the point of this is that basically the things that are in this. They serve a purpose, and if they serve a purpose today, then you can use them and you can get your money's worth. But 6 to 12 months from now, it's going to be a complete, probably changeover. So, any other questions on that note, or we'll change over? Thank you. Thank you very much.
No, I'm okay. Yes, full charge.
One of my PSAs here.
Where do you source your sensors and stuff?
There are two places, IT Studio and Seed Studio. And IT Studio you can look up, and they've always delivered, they've never ripped me off. Seed Studio was in the news today for I'm trying to think what it was now. They've come out with some kind of new something or other, but they tend to sell kits, like for $50 you can get a kit that includes heat, light, temperature. Or if you want, motion sensors, of which, you can just order electromagnetic things as well, or, on switches and buttons and stuff. But the one thing is they come from Hong Kong, and so it's, it's a week and a half.
So I have two PSAs. Harvard Heat Week is still going on. If you want to go by after midnight and hang out in front of. We don't know about Harvard Heat Week. Okay, so a very large percentage of Harvard students, undergraduates, have put together a divest Harvard group that want them to divest from
Oh, that's right, I heard about that.
Yeah.
I didn't know.
Call it large percentage.
Well,
I'm wearing the shirt, so I can speak.
but it's undergrad driven, right? Which is unique for.
Yeah.
I mean, undergrad driven.
These things tend to dissipate when you have more education.
Yeah. So, but this is getting this is getting a lot of coverage. So I figured I'd put
No,
it.
there's a band of what looks like 20 misguided souls outside
that's
Massachusetts Hall.
Yeah. My other PSA is if you want to take the Jeopardy test tomorrow night, we kind of missed it tonight. We certainly missed it last night, but you don't want to really take it the first 2 nights because all the people who are regular Jeopardy online test takers publish the answers to the previous 2 nights tests. So you want to take it the 3rd night. So this is, and of course, passing the online test is just the first of many hurdles. You have to do a little mini screen test if you pass the online test. Anyway, so those are my 2 PSAs. And I have plenty of obscure references to, I don't know if you guys know the original content that went with this picture, but Bugs Bunny says, you know, I know this defies the law of physics, but I never studied law. Still, to shoehorn this into my presentation. Lots of people, lots of great preeminent scientists have, you know, said Moore's law is dead before now. And some of them are actually in this room. Some of them are actually presenting right now. I sat on a board at Supercomputing once where we all sat around and said, no, it can't possibly survive. Well, the sand moves underneath your feet. Certainly classical Moore's law, which is Gordon Moore said in 1965 that transistor density, you know, just density per square inch or per centimeter was going to double every year. And between 65 and 72, he was pretty much on. And then it went up to 2 years. The transistor density was doubling, and there's all sorts of great charts because this is the 50th anniversary of the, you know, 1965 was the original observation. There's plenty of great articles on Moore's law and why, you know, why nobody would be talking about Apple in here without Moore's law, or why, you know, well, nobody would be talking about Intel either. So, and there's some great, I won't belabor it too much. I'll push you to some URLs. There's an article about how Moore's law is more of a basement than a ceiling. You know, Intel wanted to manage the growth of their company, not expand overheat and then collapse. So they seem to have been doing that pretty good. The 10 nanometers might be a physical limit for some things. This is the debate that's going on right now. You can certainly, an Intel process can certainly probably make a 5 nanometer wide wire right now. They just can't put them every 5 nanometers. There's like, you know, 70 nanometers between wires. But the process is when they finally get to 10 nanometers. Ambrose sent me this link on the 10 nanometer Knights Hill process. It's going to be spectacularly expensive. The NRE may not justify. Well, it probably at 10 nanometers, that may be their last financially viable process. We'll see. It is the Wikipedia actually quotes some of these guys, including Gordon Moore, that say classical Moore's law, which is strictly a discussion of transistor density, will keep going well past 2020. But this 2018 super, you know, 180 petaflops 3 years from now. That's Moore's law. That may be a little bit ahead of Moore's law. We're at like 3 petaflops for the supercomputers right now. Maybe more than that. They come out with the supercomputer list every June and November, so we'll see. One of the SoC boards I've looked at recently, this is the only one that I don't have access to. And if you guys want access to the boards I have access to, just ask me for an account. I'll show you all the boards I have access to. I'll set you up with an account. You get root access because, you know, we're only going to be using them for another couple of weeks anyhow, and then somebody else is going to come out with something vastly better. So I'm not too worried about you guys breaking anything. This is the board that IBM Zurich. You can buy one. I just haven't been able to figure out the correct path to get one. But he's one of the many guys that are looking at a chip that will commingle photons and electrons. So you probably read some of these things. You can, you know, everybody's trying to get one of the fiber optic network internet NIC architectures into a die. So if they can get, you can certainly buy SoCs right now that have a traditional copper NIC in the die and Ethernet in the die or some fabric. And now you're going to be able to get maybe Marinette right in the die, or excuse me, maybe InfiniBand, not Marinette. So InfiniBand is something, if you look at the top 500 list, 50% of all the supercomputers have migrated over to InfiniBand. Here's another architecture. This is, so those of you that have seen Thomas Summers' presentations, he said I could use this slide because he presented it at the Open Compute Summit. This one is a very specialized processor. Every micro core has memory on it. So where he's saving energy is by not moving data around. I've got a slide coming up. The places you save energy when you make your own package and die and SoC is by localization, not moving memory around if you don't have to, and fixing the network. I mean, that Intel chip that's going to show up in the Aurora cluster, they substantially fixed a lot of their network problems. They're going to integrate OmniPath right into the SoC. That Aurora computer is the first time that a chip company has won a DOE supercomputer contract. Usually they award it to someone like HP or IBM or something. Intel won that one. It's very, very unusual, and that really tells you that we're going towards SoCs as a replacement for the motherboard. Instead of a south bridge over here and a north bridge. And in the old days, we had separate graphics chips and x87s.
How many SoCs are actually in that supercomputer?
How many in the Aurora?
Yeah.
Ask me after I'm done, because
it's thousands though, right?
Yeah, that's right.
Is it tens of thousands?
Well, so the embedded Xeon 5 roadmap has so it's already 64 cores.
But I mean, how many actual chips?
Let me look it up.
Because basically, if they get this to work, right, they sort of put everybody else out of business. Because if you're an integrator, you can't just go and add all these things on chip, right?
Yeah. Well, and Intel being like one of two chip manufacturers that own that space, right? That could that could screw up the infrastructure.
Because there's none of the other companies that can add in all these cards or whatever, but you're never going to be able to beat them if they're just like, well, everything you have in a motherboard and 16 different cards we've got on the chip now, right?
Yeah, right.
It's kind of the game over.
Well, and it screws up the moonshot model, because now I say, well, I can put in this card or not put in that card, put in the GPU card, but who's ever going to swap anything out when you've got, it's at the top of the OSI layer, right? So,
yeah, that's really interesting.
Yeah.
That's fascinating.
Yeah. So right now I'm using the NVIDIA Tegra K1 for some CUDA experiments. I know Peter is too. They've come out already with the Tegra X1. Now, it doesn't look like they're going to offer it in a NVIDIA Jetson form factor. NVIDIA Jetson's really easy to work with. If you guys want an account, tell me. I'll let you out on my Jetsons. ARM Cortex A9s, or excuse me, A15s in there, so an ARM v7 32-bit architecture that you know and love. Aaron's going to talk a little bit about the ARM architecture. You log in, you start running your CUDA 6 and CUDA 6.5 stuff, and it runs like it does on the big iron discrete. Well, don't correct me if I'm wrong, Peter. It runs like it does on the big iron stuff, but there's some efficiencies that you get by unifying the architecture into a SoC. It's dirt cheap. It's $192 for a Jetson board, and it's pretty low power. It isn't the kind of low power that they estimated before they shipped this product. You have to do a bunch of command line stuff to get the ARM cores and the GPU warmed up to the rate that it runs at optimally, which is max. They did do that very well. The max frequency looks to be about the sweet spot for the CUDA cores and for the ARM cores. So those are the three architectures that I'm really bullish on. Can't get you onto the Dome server yet, but certainly, and this one too. So Linaro is the Linux for ARM company. They have partners in virtually everybody that does software for ARM. They have partnerships with ARM. ARM just doesn't produce anything. They're an intellectual property licensing company. But Linaro does. Linaro, you can download the Linaro distro of your choice. It can have it sort of server-centric or client-centric. Well, this is their first board is this high-key 96 board. And they called it 1 out of 96. I imagine they're going to have probably 10 of these 96 boards. And it was called 96 boards because so I've heard two things. Has anybody here been to the Linaro events? Because I haven't verified which one of these is true. They only made 96 of them. That's possible. And I have one, so if you want an account on one. The other thing is 96 is 32 plus 64. And you can run, so these are ARM V8 boards. They're ARM Cortex A53s, 8 ARM V8 cores for $129, which is pretty mind-blowing. Our AMD rep isn't here, but an equivalent dev board from them, 10 times the price. I mean, and that's the academic discount, $1,500 for the Seattle dev board. Now, it's a little bit better than the $129 board. And this thing is so new that the developers are busy still kicking out some of the bugs. But it's a great development path, and it's spectacular to see Linaro saying, "Well, we'll support this. This is our first hardware effort. We'll support it and push things out." And so if you guys want an account on this, I can give you one on that too. I haven't really been able to tax it too hard yet. I've had a couple of things which I'm not quite sure what the bug reporting process is for Linaro, but we better figure that out. Every now and then I find out something that they should know about, because High Silicon, which is making the ARM Cortex A53 for these boards, they're going to want to know. They've got a very broad, wide roadmap.
We've got a mailing list in the forum that's into bugs.
And it's like just a mailing list, right? Yeah, because they had a table at the Open Compute Summit, and I knew more than they did. It was really bad. It was like, hey, I saw your forum, but it's very hard to search the forum.
So the mailing list is better.
Yeah. Okay, so I think I've made a provocative, compelling case for why HPC is embedded and why SoC is going to zoom past existing architectures. Certainly, if you want to build a data center in the future, and you've got a budget, so if you have a budget, if you have a cap, then you've got to look at some of these eHPC architectures. Open Compute has a number of standards, some of which are very mature, some of which are in progress for rack, for power, for network. Their power specs bring DC, very high voltage DC down very close to the chip. They have at least one standard that's 13 kVA to the rack, and then it gets distributed down. And they have motherboards designed that only use 2 voltages. Open Compute is very aggressive about analyzing the trade space for the data center of the future. Thomas is the head of the Open Compute HPC subtrack. So we can get, if you're interested in HPC, I know HPC is a bit of a fringe part of the whole SoC ecosystem, but if you're getting interested in talking further about HPC, every time a new SoC comes out with HPC with one other architecture in it, like an FFT accelerator or a streaming accelerator or something, it's a huge windfall for us, because the code is pretty portable. You every now and then need to change a construct, but you know, using one of the advantages of the Tegra K1 is your memory is shared between CPU and GPU if you use the right CUDA calls, and that saves you here again the data movement penalty hitting the PCI bus. There's no PCI bus on the Jetsons. Well, actually, I think there is, but nobody uses it. They basically try to do everything on die in memory. Here's a list of some of the folks that have moved towards SoC. There's, besides the RISC architecture that Aaron's going to talk about, there's a couple other people in that space. The low risk design, not sure how it differentiates too much from RISC-V. Maybe you were at the conference, maybe you can say something about low risk. You guys, probably quite a few of you have seen the Adaptiva Epiphany chip that the guy from Adaptiva has come and talked about. So he's very much of a SoC fan. His development system was, you can buy a Z board or a micro Z or a Zybo for around $200. It's got a Zinc 7000 Xilinx FPGA on it with 2 ARM Cortex A9 hard cores in it. So you log into that, and whatever you want to develop with, as long as it's on the other end of the AXI bus, you can build in some features and then figure out some way to integrate it as a board. And that's exactly what Adaptiva did. They put their Epiphany 3 chips on the Parallella board with the Zinc 7000. So he did all this development on a Z board. When they went to develop, he bypassed the AXI bus and got his chip on the board. I won't belabor this too much. The 3 things keeping us, this is a slide I got from the guy that writes most on system on chip and HPC is the head of NERSC, John Schalf, and he has done quite a few of the SoC conferences. He had a guy come to our conference that I'll put a plug in at the very end there, high performance embedded computing. But he really details the 3 walls that you hit. Power wall, you hit that with everything, including desktop, trying to find ways to better use the power. Instruction level parallelism wall, this is something we've been wrestling with in HPC for a while. One of the reasons RISC is having a sort of a comeback is the shorter pipeline. And then, of course, the von Neumann bottleneck, the memory wall. A spectacularly large percentage of the PC business has been devoted to trying to find ways to make up for the lack of memory performance for the pace of CPU performance thanks to Moore's law. I mean, we double buffer, we prefetch, we're doing all sorts of crazy stuff. Multiple lanes, just to be able to make sure that our slow memory can keep pace with our fast CPU. Yeah, so on the NEO slide, I spoke of the value of memory proximity and locality. Very much true with networks. If you can find a way to get your network into the same package as your CPU, you've really solved half the problem. This is I'll bring up, to answer some of Peter's questions, I'll bring up the Aurora slide again afterwards. This is substantially where Intel innovated to get OmniPath 2 into the die. Intel has quite a few fabric and network topologies that they can look at now, and I guess they chose OmniPath 2 for the 2nd generation. Nice. I'll look it up. We gotta look it up for Logan too. So this is one last plug. I don't see Tom Metro here, but Tom posted on the.
Tom's right here.
Is he? Oh, so Tom put on the hardware subgroup at BLU a wonderful article that Bunny Huang, who's involved with the Low Risk Project, did, and how the Moore's law starting to tail off is actually favoring pushing down innovation to the startups now, and you see Kickstarters with guys with innovative chip designs right now, and if they get to a certain threshold, then they can run over to TSMC and say, hey, can you print 100,000 of my chips? And so it isn't quite the $1 million gambit it used to be. Our own, Adaptiva in Lexington. It's a 2-person company. That's something of a proof of concept right there, that he went through the Parallella on Kickstarter process, got enough people to buy into it that he was able to afford a first shuttle run of his Epiphany 3 chips. And it's still a large run. I mean, he's got some on the shelf. If you want any Epiphany 3 chips, I'm sure he'll sell you some. But this is encouraging. I only have one slide from the article that Tom linked from the IEEE Spectrum. This month's IEEE Spectrum had a number of Moore's Laws articles, so I thought this was interesting. And finally, here's the plug for our local conference. So high performance embedded computing, extreme computing, has a lot of embedded subtract presentations. You'll get people talking about, what you can do on the Tegra K1 there, for instance, and there are a lot of people get up there and talk about their designs that don't have any spindles. It's all solid state. So a very, very interesting conference. It's only been an IEEE conference for a couple of years, a Lincoln Labs conference, but it's coming up. The poster deadline is after May 15th, but the paper deadline is May 15th in case any of you want to contribute. So I'm going to hand off to Aaron. We wanted to leave some time at the end too. We're on about some of the specific SoCs that we discussed.
I'm just cue for applause now.
Oh, yeah.
I wonder what that awkward pause is for.
Should be both.
Yep. Cool, thanks. All right, starting the timer so I can't go over. Okay. So my name is Arun Thomas, and I'm going to be talking about a couple of the kind of interesting architectures that are out there in SoCs, ARM v8 and RISC-V. So Kurt and Brian kind of teed me up. They talked a little bit about ARM and a little bit about RISC-V, so that was helpful. So the two architectures I'll be talking about, ARM v8 and RISC-V, they have a lot of similarities in terms of the architecture. I've been working with both of them recently. I'm giving a talk at the Embedded Systems Conference in May. It's in Boston about ARM v8, so I figured I'd grab a couple of the slides and kind of talk to you guys a little bit about ARM v8. That talk's still in progress, but there's some content I can share with you. And then I'm also going to talk about RISC-V, which is a relatively recent ISA. I think it was announced at the end of last year, and I went to the RISC-V workshop. The first RISC-V workshop is in Monterey around January, and so I can share some of the things I learned there. And so since these ISAs share a lineage, RISC, MIPS, they have a lot of similarities, and I'll go through them. But they have sort of completely different models. So ARM is a licensed ISA, and I'll talk about what that means. RISC-V is an open ISA. So start with ARM. So ARM, you guys probably have multiple ARM devices. It's hugely popular in embedded systems, and phones, tablets. It's starting to move into general purpose computing. So laptops, server platforms, high performance computing, especially with the 64-bit architecture. ARM has an interesting business model. They don't actually manufacture any of their chips, unlike Intel. Intel fabricates their chips. They have the best process engineers basically in the world. So instead what ARM does is they license their architecture and their cores to different SoC manufacturers like TI, Freescale, and people like that. So quick overview of the ARM architecture. So ARM stands for Advanced RISC Machine. It used to be the Acorn RISC Machine. RISC stands for Reduced Instruction Set Computer. So simpler instruction sets, they're load store architectures. You can't do memory-to-memory operations. ARM's Big Indian or Little Indian. Little Indian's more common. And there's been several versions of the ISA over the years. The two current ones are V7, V8, the V7, V8. V7's 32-bit and V8's 64-bit. So most of the phones and tablets that you'll see are 32-bit. Recently, there's been some 64-bit hardware getting out there. ARM has a few different architecture profiles. ARM, which spells out ARM, which is kind of clever. So the application profiles would all be talking about. These are the things you find in your phones. The real-time microcontroller and microcontroller profiles are for your kind of like embedded devices. So the device that Brian talked about was one of the M profile devices. So ARMv8 is actually pretty new. So ARM began work on it in 2007. They started designing the ISA, and they announced it at TechCon 2011. And the actual specification didn't come out till around September 2013. And the first hardware didn't ship until September 2013, and that was the iPhone 5S was the first commercially available ARM device. So, and that had the A7 chip in it. So ARMv8, what is it? It's a 64-bit architecture. Its official name is ARC64, which is a little bit of a mouthful, which stands for ARM Architecture 64. Colloquially, a lot of people call it ARM64. And it has a full MMU supported data profile, so you can run like Linux. It has full virtual memory support. And ARMv8 supports both instruction sets. You have a 32-bit instruction set that's compatible to ARMv7. And then you have the new 64-bit instruction set that's legacy-free. And ARM basically cleaned up a lot of the warts in their instruction set architecture with A64. Another interesting thing is that the 32-bit ISA is actually optional, so you can have just a 64-bit ISA, and that's compliant. So this is a quote from one of the lead ISA architects at ARM, and he actually used to be a former MIPS designer, so I kind of dug up this presentation, and he says in his slides, says, doesn't it look, he asked the question, doesn't it look a bit like MIPS? And he says he couldn't possibly comment because, but then later he goes on to say that, yeah, it is, because it lost some of the idiosyncratic ARM things, and it looks a lot like your conventional RISC architecture. So it looks like MIPS, Alpha, PowerPC, and HPPA. And all because it's descended from the Stanford RISC and Berkeley RISC projects. So some of the main improvements with the ARMv8, it's 64-bit, so that means you have 64-bit wide registers. You have more usable registers. So ARMv7 had 16 registers, but that included the program counter and the stack pointer, so only 14 really usable registers. With 64-bit, you get expanded address space. You can have more memory. And they cleaned up the instruction set a lot. So the instructions are simpler. It's easier to make high performance implementations. The exception model, if you're an OS hacker, is simpler. And they also standardize the platform. So I don't know if you remember a while ago, there was this thing about Linux was very unhappy about the proliferation of ARM SoCs, and like it was just being a really like a pain to handle. So one thing that ARM did well here is they started to standardize the platform. So on Intel, you basically have kind of your standard PC platform, and so ARM's starting to do that. So you have a generic interrupt controller. You don't have an interrupt controller for every different SoC. You have generic timers, generic watchdogs, generic UART, and all of that. So here's a list of a bunch of the ARMv8 hardware that's out there. You probably can't read this, but so the iPhone, the iPad, 64-bit hardware. The Google Nexus 9 tablet is also ARMv is a 64-bit, and it uses an NVIDIA SoC, the Tegra that Kurt talked about. You also have the Applied Micro Mustang. That's an interesting board, and the KVM Thunder X, which I don't think has been released, but it's also interesting. So all of these boards are custom cores. So each of these manufacturers designs their own core. They grab the licensed instruction set from ARM and design their own chips. What most people, so there aren't many people who have these architectural licenses. They're fairly expensive, I think, and hard to negotiate. Typically what happens is typically SoC vendors will just grab the Cortex core from ARM and then just integrate that into their SoC. So that's my IP blocks, and there you go. So the people who've done that, the Samsung Galaxy S6, it's a Qualcomm SoC. It uses the ARM Cortex cores. The 96 board's high keyboard that Kurt talked about from Lenovo, it uses the high silicon SoC, but that uses the Cortex core.
So the S6 is 64-bit?
Yeah, it's 64-bit. Yeah, it's one of the first 64-bit phones.
Yeah.
I think also one of the Galaxy Notes also has a 64-bit core. The ARM Juno board that Kurt also mentioned, a bit more expensive, or the Opteron, I think Kurt mentioned. Yeah, both of them.
Opteron.
Yeah, AMD's making ARM chips now.
Yeah, they're calling them Opteron A's.
Yeah.
Okay, yeah, I was gonna say,
Yeah, so I mean, it's kind of a brave new world, right? You've got like people like AMD making ARM
Did
chips.
Samsung do a custom core too, called something else?
Yeah, well,
So it was E
Samsung
or something,
typically
right?
uses the Cortex chips. Like they'll have their SoCs. So in the
They had one that
S6,
was with E, it started with E, I can't remember the name of it, it was their own chips.
yeah, so it's the Exynos, but
Yeah.
they use they
That's
typically
custom
use,
core, right? Or-
it's a custom SoC, but they typically use the core from ARM. So only a few people actually,
Okay.
as far as I know, they like, at least for the S6, they grab the ARM cores. For some of their other cores, it's possible that they design their own cores, but typically they'll just grab them from ARM. The Easy Chip is also interesting. They're a local, well, so there was a company, Tylera, which is a local company, and it got bought by Easy Chip. So they have these like really dense compute, like hundreds of cores on a die kind of thing. So it's kind of cool.
So the former CTO of Tylera now works for ARM.
Does he? I didn't know that.
Yeah.
Okay. Cool.
Now, doesn't Qualcomm go up there somewhere?
So Qualcomm, yeah, so Qualcomm does not have a 64-bit custom SoC. They've licensed the Cortex. I think eventually they will. I think basically what they want to do is get a chip out quickly, so they just grab the ARM cores. But typically they do have an architectural license, and typically they do have their own custom cores. Right? So I think in the future they'll probably have custom ARM V8 cores. So yeah, here's a few of the cores. So you've got the ARM Cortex that a lot of people use, Apple Cyclone in the A7, A8, and the A8X. NVIDIA's Denver is found in Tegra. I don't actually know how to pronounce it. KVM ThunderX, Applied Micro has the XGene and the Helix. The Helix is supposed to be their embedded 64-bit chip. The XGene is meant to go in servers. And Broadcom has a Vulkan SoC that has been announced, but I don't think it's come out yet. So I'll quickly go through the ISA, and I might skip some of these details because they're a little bit kind of nitty-gritty, but so it's kind of a standard RISC ISA. You've got a 31 64-bit registers, X0 through X30. You can also access them as 32-bit registers, so if you use the W0 to W30. Then you have a program counter, stack pointer, frame register. It looks pretty standard. You've also got floating point vector registers, V0 through V31. And here's some of the assembly syntax. It looks pretty similar. It looks like a standard RISC ISA. This program just moves, it adds two numbers. So you've got data movement, you can add numbers, things like that. And you've got your standard load and store if you want to load from store to memory. And then you've got control flow instructions like branching and return, things like that. And then, so that's the user side. On the system side, for if you're a kernel person, then they have a bunch of system instructions and registers, and they kind of look like the standard RISC stuff. So you'll have instructions to set up your caches, your memory management unit, the VNR controller. This is the instruction to set up the page table, things like that. There are multiple exception levels. There's 4 of them. There's one for the application code, kernel code, hypervisors. ARM has this thing called trust zone where you can have a secure monitor. So higher levels, higher privilege. This is fairly standard for RISC cores. There's also this thing called interprocessing. So you can run 32-bit and 64-bit code on the same V8 core. So you can actually mix them within the same process. You could do this with ARM v7. They had this 16-bit instruction set called thumb and a 32-bit instruction set called ARM. And within the same process, you could jump to between 16 and 32-bit. You can't do that between 32-bit and 64-bit code. Instead, you have to kind of trap into the kernel. So you can have 32-bit processes and 64-bit processes, but you can't have one process that has both of those. And then, yeah, you can have a 64-bit kernel that can run 32-bit and 64-bit apps. You can have a 64-bit hypervisor that runs 32-bit and 64-bit kernels. So they've kind of kept compatibility that way. You've got your standard exception types, memory boards, system calls, interrupts. ARM has this thing called fast interrupts, which are higher priority interrupts. This looks pretty similar to ARM v7. It's just a little bit, it's cleaned up a bit. ARM had this thing, ARM v7 had this thing called banked registers, which is sort of complicated. Virtual memory, it's 64-bit address, but only 48 of the bits are used. So that gives you an address space of 256 terabytes, so decent amount of memory. Paging support, 3 or 4 levels of page tables. There's a hardware managed TLB, so the MMU will handle the page table walk and TLB miss. There's kind of nitty-gritty details. And then there's a bunch of kind of basic page sizes. You can have your 4K, 16K, or 64K page sizes. Those are the kind of basic page sizes. If you actually want to get more of the nitty details, the place to go is the ARM Architecture Reference Manual. It's 6,400 pages or something like that, so you're not going to read it cover to cover, but it has all the details you want. And it's called the ARM, cleverly, I think. So, and then if you want details on your specific processor, you can look at the Cortex-A processor manual. For your SoC will have a technical reference manual, so you can look at that. If you've been doing ARM hacking, there's a porting to 64-bit ARM white paper, which is fairly short and will kind of get you up to speed. And then if you're doing ARM v7 hacking, these docs haven't been updated for 64-bit ARM, but they're fairly useful. The ARM Cortex-A series programmer's guide is a good read. It's a few hundred pages, but it gives you all the information you need without reading all the pages that are in the ARM. And then there are also migration guides from MIPS, Power, and IA32 to ARM. So if you're doing the ARM hacking, these guides are fairly useful. Okay, so that's ARM. And then I'm going to talk about RISC-V. Do you guys have any questions about ARM? All right, so kind of interesting. So the RISC-V people, they put this white paper out. They published a microprocessor report, which a lot of people read in the industry. And it was titled "The Case for Open Instruction Sets." And the quote was, "Given that the industry has been revolutionized by open standards and open software, with networking protocols like TCP/IP and operating systems like Linux, why is one of the most important interfaces proprietary?" And so they're talking about the instruction set architecture. And they were sort of kind of indirectly going after ARM. ARM posted a rebuttal also in my microprocessor report. Their rebuttal was called "The Case for Licensed Instruction Sets." And they said that the ISA license is a consistent baseline that maintains compatibility, enabling an ecosystem to coalesce. So it's sort of two different models. ARM's done a lot with open source, and they've got a lot of kernel hackers and compiler hackers that have been great for open source. But if you actually want to build a core, if you're a hardware designer, you have to license the core from them. The nice thing about RISC-V is you don't have to do that. So if you're an open source hardware person, RISC-V might be a little bit more interesting to you. Or if you have a lot of money, I mean, you can license the ARM. You can get an ARM license, so maybe it doesn't matter. So here's the stated RISC-V project goal, and it's not super ambitious. This is from those slides. It's to become the industry standard ISA for all computing devices. So, I mean, they're not messing around. So here's a little bit of the history. RISC-V comes from Chris Desanovich and David Patterson. If you've been around the industry and if you're into computer architecture, the name David Patterson probably stands out. So he's the guy who came up with the first RISC processors. It was him and John Hennessy. He's got the kind of V-book for computer architecture and computer organization, also with John Hennessy. He also mentored RAID, so he's a pretty big guy in computer science. So they have a pretty well-known architecture group, and so they built a lot of these chips, and they began looking for a sort of common ISA for their research in 2010. And so x86 and ARM were kind of the go-to choices. I mean, they're kind of like the main architecture out there. But the problems with them is they're sort of complex, especially x86. There's so many different instructions, and there are the IP issues. You'd actually have to license the core. So then they decided to develop their own ISA in December of 2010, and then 4 years later they released the user spec, frozen user spec, and they sort of taped out a bunch of RISC-V chips along the way as they kind of gained more experience, and they continue to do so. So I'll quickly go over RISC-V. It's an open instruction set architecture, so as I said, you don't need to license it. it's a specification, so it's not a particular implementation. So you can have commercial RISC-V implementations. You can have open source RISC-V implementations. Berkeley has an open source RISC-V implementation, which you can grab off GitHub, called Rocket. And then Kurt mentioned some of these RISC-V projects. So there's a low-risk project, which was started by two of the guys from the Raspberry Pi Foundation. They're the guys who started Raspberry Pi. And so they describe the project as sort of Raspberry Pi for grown-ups. So they're building a completely open hobbyist board. And they've done some interesting things in terms of the security architecture and the I/O architecture. And if you want to read more about that, they have a white paper that they released a few months ago. And they're doing some pretty interesting research in computer architecture. So their goal is they have FPGA prototypes, and their goal is to ship production boards in 2016 or 2017, hopefully. BlueSpec, a local company, a local EDA company, they're also developing RISC-V cores and IP. We use them internally for some of our stuff, at least their EDA tools. The government of India, this is interesting. So they're trying to bootstrap their semiconductor industry. So they've adopted RISC-V as standard ISA for all of India. And so they're building a bunch of RISC-V cores. So IIT Madras is kind of leading the effort. And so they're building 6 open source cores, from microcontrollers all the way to supercomputers. So it's a really big scale project. I talked to that project, and yeah, it's pretty impressive. To Kurt's interest, Lawrence Berkeley Lab is creating this open SoC fabric. It's a network on chip generator, and that's pretty interesting as well. So there's a lot of interesting projects that are coalescing around RISC-V. As I said, it's got the RISC lineage, Berkeley and Stanford RISC. The nice thing about RISC is that it's easy to implement and efficient. So it looks a lot like ARM v8 and MIPS. So if you compare the instruction sets, there's a lot of similarities. The nice thing about RISC-V, if you're an architecture person or a hardware person in general, is that it's designed to be extended. So you can add new instructions, you can add accelerators, IP blocks fairly easily. And they've designed it to be the common ISA for basically every IP block in the SoC. So there's 3 base integer ISAs. To call yourself a RISC-V core, you have to implement one of these. So there's 32-bit ISA, there's a 64-bit ISA, and there's also a 128-bit ISA, which is kind of good. So there's only been implementations for the 32-bit and 64-bit. So the nice thing about it is a very small ISA. So if you have a really small embedded microcontroller, like a disk controller or something like that, you only have to implement 40 hardware instructions. That's fairly doable, or even a course project that's almost doable. So you have this base instruction set, then you can add things on top of that. So if you need a multiplier, you'll have the multiplication, BM extensions. If you need atomics, you'll have the A instruction, then you have floating point, double precision. So you can sort of layer, depending on what your core needs, you can sort of layer different extensions on top of it. So it's fairly nice because it's configurable. So you can kind of use it in a lot of different places. So this is why the government of India can start looking at the same ISA for microcontrollers all the way up to supercomputers. So the ISA looks a lot like what I showed you with ARM v8. So it's a fixed 32-bit instruction, 31 registers, which is the same. The instruction encodings are inspired by MIPS. The privilege spec, if you want to do any OS hacking, is under development, but one of the drafts I saw looks pretty similar to ARM v8. There's some differences in the virtual memory architecture, but it looks pretty similar. If you want to learn more about RISC-V, you can go to the website. You can look at some of the specifications. As I said, the user level spec is out there. The slides from the RISC-V tutorial at HPCA 2015 is up there. I went to the RISC-V workshop. The slides were pretty much the same. These are just updated. And all the code is on GitHub, so you can clone the code. And I made some minor contributions. They're pretty open and happy to have people contribute. So if you're going to hack RISC-V, there's a number of emulators you can use. Spike is the official emulator from Berkeley. QEMU, there's a RISC-V model. The JavaScript emulators, you can actually do Linux on RISC-V on JavaScript, which is kind of cool. And then there's a bunch of FPGA platforms from Xilinx that Kurt mentioned also, like the Zybo and Zboard. I have one, and it's kind of cool to play around with. And then you can wait a couple of years, and low risk will come out. And just to show you guys RISC-V booting in the browser. So this is Linux booting up on emulated RISC-V in my browser. So it's kind of cool. So you can play around with that. Summary, yeah. So ARMv8 and RISC-V are both fairly interesting architectures. Fairly recent, and they have a lot of similarities. Completely different licensing models, but both cool. And we're hiring. So if you're a CS person or EE person, send your resume my way.
I'm sorry, can you talk again about the RISC-V hardware that you showed? Like you can, you can't buy a chip.
You can buy, so you cannot buy a fabricated chip. So Berkeley has fabricated a bunch of test runs that they've used for their research. What you can do is you can get an FPGA and you'll load a bit stream on there. So, or you can hack out a QEMU, like a software emulator. But I mean, in 2 years' time, hopefully low risk will come out, and then you can have a Raspberry Pi style board with RISC-V chip in there.
So you won't get the energy efficiency performance out of a Z board, but you'll be able to run all your code on it.
Any other questions?
Do you know anything about some of the, I don't know if any of these products are out yet, but somebody's coming out with a SoC with some number of ARM V8s and ARM V7s on them, so that you can do like big little sort of a workaround to the internetworking.
I haven't heard of those. I've heard about Big Little, just V8, but yeah, I mean, that would make sense actually.
Yeah, I think maybe TI, but I don't think any of these products are out there.
I could see it, yeah. I haven't heard of any V8 chips from TI yet, but yeah, it would make sense that they would do something like that. Thanks.
Thank you. Is that Rocky?
No,
I thought they were banned in this place.
he thought I was dead.
I thought that too.
Let me have a show of hands of who's going to the brewery over here. Steve, you're going. I forgot your name again. Hurry. So 2, 3, 4, 5, 6. You going to the brewery? 7. Kurt?
Yep.
8. So there are 8 of us. Who is going to walk the brewery?
This will stop the broadcast, huh?
What?
I guess I can stop the